Hello everyone, yes Shibras. So you will be understanding this bit thing if you have watched the first part of this video. Then you will be understanding this. Fine. I think everything is fine. Okay. So are you listening? Am I audible? Please tell me. Am I audible? Am I audible? Yes or no? Yeah, fine, very good. Okay, then we are starting. So in the last video we talked about the energy of rotational energy level from classical mechanics. We calculated, and the value was E rotational equals to half I omega square, and also we calculated the I, that is called moment of inertia, in the last video. Fine. That was our moment of inertia. Fine. I was our moment of inertia, and we calculated the value of I, and the I was coming out I equals to mu r square. So we have calculated the final expression of energy level for a rotational molecule, and that calculation was done by using classical mechanics, right? Classical mechanics, energy from classical mechanics. Fine. Now in this video we will be calculating the value of energy from quantum mechanics, and that will be everything regarding this video. In the next video further, that will be the last video on rotational spectroscopy, and in that video we will be talking about some application part of rotational spectroscopy, okay, or some other features. Got it? So in this video we will be calculating this energy from quantum mechanics. Great. So let's start then. So what will be the energy of rotational molecules according to quantum mechanics? Because in the last video I told you that energy E becomes E rotational, that becomes half I omega square, and this value I am getting from classical mechanics. Okay, classical mechanics, right? Yes. And in this video we will be talking about energy value for quantum mechanics. So you know, in case of quantum mechanics, dual nature, you have listened about this word, dual nature, right? According to de Broglie wave nature, de Broglie theory, de Broglie hypothesis, we know about dual nature. So we have already seen in the last video that how your molecule behaves like whenever they are rotating, that creates a wave like properties. I told you about the rotational properties of the molecule. So whenever they are rotating, they are giving me this kind of wave, and this wave, if I consider, okay, if molecule is showing this kind of wave, then I can say the molecule would have little bit some kind of wave function psi, and if I have some kind of wave function, then I can apply Schrodinger wave equation. Yes, I can apply. So if I apply Schrodinger wave equation in case of rotating molecules, I will be getting this expression, del square psi plus 8 pi square m divided by h square e minus v and psi equals to 0. You know all the terms involved over here, you know about all those terms, right? So if you consider, I am especially representing this E, V and this M. All other terms you know already. So M means mass of the particle which you are considering. If I am considering molecule, then M will be the mass of the molecule. E is what? E is total energy. Total energy, right? Total energy. In this case, your E will be what? Rotational energy. Rotational energy. Great. In this way, your V is about only potential energy. Okay, remember, only potential energy. Fine. So this energy E term is including total energy, and this V is including only potential energy. So total energy means what? Potential energy plus kinetic energy. Fine. So here this E incorporates potential and kinetic energy, but V incorporates only potential energy. So from total energy, I am subtracting the potential energy. So if I do that, what I would be getting? I would be getting the value likely to be this. I would be getting the value likely to be this kind of equation. And already I told you, we are discussing what rigid rotor model. Don't forget, we are discussing rigid rotor model. And according to this model, the bond length of molecule is unchanged every time. Whenever the molecules are rotating, the bond length, this R distance remains unchanged. If its bond length remains unchanged, that means this potential energy becomes zero. So this, according to rigid rotor model, the potential energy of the molecule is zero whenever they are rotating, because the bond length is remaining unchanged during their rotation. So this value will be zero, and E actually our rotational energy. And as in the last video I have already shown you that your mass, whenever molecule is rotating, your mass and the molecule will have a moment of inertia. So you will be incorporating moment of inertia as well in the place of this mass. So now if I do this, if I change my Schrodinger equation by considering mass, total energy and potential energy, what will be my value? As my potential energy is zero and my mass is converting to moment of inertia of the molecule, then I will be getting this kind of expression: del square psi plus 8 pi square I, that is called moment of inertia, divided by h square E rot then psi. So why I have taken E rot? Where is V? V is 0 because the molecule is following rigid rotor model. Got it? Simple. So because of that, what happens? Because of that, simply, if you solve this expression, I am not going to solve it. Nobody will solve this expression because the solution will be too tough solution. For that you have to understand polynomials, a lot of things. Even nobody will suggest you to understand the solution. So after solving this, the result that you will be getting is this. Your E rod value will be, E rod also represented through EJ. Okay, E rod value will be what? E rod value will be h square 8 pi square I multiplied by j into j plus 1, and it is E, so the energy unit will be joule in SI. Okay, and this J, if you consider this J is basically called, do you know what? Rotational quantum number. And this J has value 0, 1, 2, 3, dot dot dot, this kind of integer values. This J has this kind of integer values. I think you can't see some portion of this part, right? Because of me. Yeah, I am making myself smaller a little bit. Got it? So this J is called rotational quantum number that has value 0, 1, 2, 3. Okay, and as you are having some specific values of J, so your rotational energy level will be quantized energy level. Okay, quantized energy level. That means you will be having some specific values of rotational energy. Quantized rotational energy levels. Right? That's all. Perfect. Now, this E energy is representing through joule unit, but in spectroscopy generally energy is not represented through joule unit. No, energy is represented through centimeter inverse, wave number. So how would I do that? Simple, it's very simple. So you already know that E equals to h nu from Planck's law, right? And h nu equals to hc divided by lambda. And from here you know hc and 1 by lambda means nu bar. So I told you this nu bar, that is called wave number, that is useful to represent the energy in case of spectroscopy. It's okay. So in spectroscopy we incorporate, we represent energy in terms of wave number. Remember, in spectroscopy we represent energy in terms of wave number, right? nu bar. Great. I hope you understood, right? So if I want to represent this energy with wave number, so now calculate wave number from here. So wave number will be what? Nu bar will be E divided by Hc. So if you divide your value, divide your energy through Hc, you will be getting your energy value in wave number, right? That's all. This E rotational value, if you divide it through Hc, you will be getting your value in wave number from Joule. Simple. So therefore your wave number, that means energy in terms of wave number, will become what? That will become E rotational divided by Hc, and that will become equals to what? Here it is H square 8 pi square I think, yes, multiplied by 1 by Hc j into j plus 1 centimeter inverse. If I represent my wavelength in centimeter, then I represent my wave number as centimeter inverse. Okay, got it? So it's your equation. Therefore we can write nu bar will be equals to, if you do the calculation, you will be getting H divided by 8 pi square I c, yes, j into j plus 1, and this is the value in centimeter inverse, and where this j equals to what? You know, 0, 1, 2, 3, comma dot 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 integer values. Fine. And now according to this equation, if you do your calculation, if you want to get your rotational energy level, that I told you already, your rotational energy level will be quantized. How can you show those? How can you show those? Great. Fine. But before I go to those energy levels, I want to tell you that you can look at this term, H divided by 8 pi square IC. This term is basically called the rotational constant. Got it? Therefore I can write my expression once again, Bj into j plus 1 centimeter inverse. This is my final expression, where your B is called rotational constant. Your B is called rotational constant. Great. I hope you got it. Fine. Now finally your rotational constant would have unit same as the unit of nu bar, because here this has no unit, so the unit will be of this will be the unit of this. Okay, because this has no unit, because it has only values 0, 1, 2, 3 like that. So because of that you will be having your values, unit of rotational constant will be centimeter inverse. So remember, in examination you may be asked that what is the unit of this rotational constant B? Okay, so that's important. Now as I already told you, this j has value 0, 1, 2, 3, 4 dot dot dot, and because of that you will be getting quantized energy level. You will be getting quantized energy level. Fine. So how would you get those? It's very simple. So let me draw a plot for this. First of all, I am putting value of j over here, then I am putting value of nu bar over here in centimeter inverse, definitely. Okay, then I am putting energy level. Okay, then I am putting energy gap. So all these things I will be showing you right now. Fine. Great. So now let's check. First of all, value of j is 0. So if you put value 0, so put it 0. If it is 0, so multiply with this and this. You will be getting nu bar, that means energy will be 0. So value of j 0. Value of nu bar will be what? Again 0. Perfect. Similarly, if you put value of j equals to 1, so it will become what? 1 plus 1, 2b. Perfect. 2b. Value of j equals to 1, you will be getting nu bar value 2b. Okay. Then after that, if you get value of j equals to 2, that means 2 plus 1, 3, 6b, right? That means this is 0 to 2b, 0 to 2b gap. So 2b to 6b will not be here this gap, it will be more gap, right? So because of that I am writing 6b over here. I am giving more gap, right? More gap. I am giving more gap. Yeah. I am putting 6b over here for j equals to 2. Similarly, if I put j equals to 3, then what I will be getting? Like 0, 1, 2, 3, my gap will be more. So 3 plus 1, 4 plus 3, 12. 12b. Then if I put 4, my value will be further more. And my value will be 20b. Got it? So if you look at, this is your value of energy. These are your energy values. So these energy values are quantized values. Why? You cannot get values 15b. No. You cannot get values 10b. No. You will be getting this specific value based upon this j value, right? That's why as you are getting some specific value, as you are getting some specific energy value, that's why it is called quantized energy state. Okay? And this energy state can be represented through this energy level, this with this, this with this, and finally this. And if you see that energy level, the distance, the gap is increasing every time. Okay, so it is 0 to 2b distance, 2b to 6b, how much distance? 2b to 6b, 4b distance. Similarly 6b to 12b, how much distance? 6b distance. 12b to 20b, how much distance? It is 8b distance. Got it? It is 8b distance. So this is how this thing works. So can you tell me, can you give me the confirmation that did you understood this till this? Can you tell me, did you understood till this? Till then I am recharging my Apple Pencil, so I need that one. Fine. So can you give me the confirmation? Yes or no? Can you write in the comment box? Yes or no? Yes or no? Yes or no? Tell me. Are you getting this? This thing is very easy. Only mathematics are there, but yeah, believe me, these things are very easier. Very easy and very easy. Spectroscopy, physical spectroscopy is not as tough like organic spectroscopy. You may have problem with organic spectroscopy, but for physical spectroscopy you won't have any problem, because here only logic, mathematics is there. So wherever mathematics is present, so you shouldn't have any kind of theoretical concept. Every result, every conclusion you will be getting through mathematics. Fine. So that's how you will be representing your spectra. Fine. Now come back. Now if I tell you these are my energy levels. Now my question is, what is the energy gap? So energy gap between these two energy levels is what? These two energy level is 2b. Energy gap between these two energy level is 4b double. Energy gap between these two energy level is 6b. Energy gap between these two energy level is what? 8b. Look at this. Energy gap is increasing. Energy gap is increasing every time. Whenever you are moving from left to below to above. Whenever you are increasing your j values, your energy gap is increasing, right? Fine. Very good. So what conclusion you are getting from here? What conclusion you are getting from this plot? So you are getting two conclusions. You are getting two conclusions. Number one conclusion is that all the energy levels are quantized energy levels. Because of that I am getting some specific value. I am not getting any intermediate value. So quantized energy level concept. Quantized energy level concept, right? First thing you are getting this. Second thing that you are getting is about what? That energy gap is increasing whenever you are increasing j values, right? So j value is proportional to actually energy gap. Okay. So if you increase your j value, energy gap will increase. Now here one concept generally comes that is called 0 point energy. 0 point energy. So what is 0 point energy? How can you show from this plot? It is very simple. 0 point energy is totally simple. What you need to do, you have your energy expression. In this energy expression, this is your variable. That means this is the thing that you are changing every time to get your quantized energy levels, right? So these variable, the lowest value of this variable is 0. Okay. So if you put the lowest value of this variable in that energy expression, what you are getting, which value you are getting? You are getting 0. So let me put this value. So your energy expression is nu bar equals to 2bj into, I think it is okay, bj into j plus 1, bj into j plus 1. So if you get this value, this centimeter inverse, okay, now I am doing what? I am putting the lowest possible value of j. So for lowest possible value of j, what is your energy values? That if you are putting this, nu bar will be b into 0 plus 1 centimeter inverse. That means your nu bar becomes 0. So nu bar means what? Your nu bar means energy in terms of spectroscopy, in terms of wave number. So if you represent your energy through nu bar, you are getting 0 value. That means for this rotational level, or I can say for rigid rotor model, I have no 0 point energy. 0 point energy means you have to have some value of energy at the lowest level. So this is your lowest energy level, okay? This lowest energy level has 0 value. This lowest energy level has 0 value. That means according to this, if j value is 0, lowest energy level will be 0. So that means according to rigid rotor model and according to quantum mechanics, you don't have any kind of 0 point energy. So therefore there is no 0 point energy. Therefore there is no 0 point energy. Okay, so if you have 0 point energy, then you have to have some positive value at positive energy value, okay, for which you are having different energy values. So for j you are getting different energy levels, but if you put the lowest value of j, you are getting lowest value of energy, that is 0. So if it is positive value, the lowest value is positive value, then it will be you will have some 0 point energy value. But as it is 0, so you won't have any 0 point energy. Got it? Yes or no? Tell me in the comment box, yes or no. Got it? Yes or no? So in this case, in the rigid rotor model, you won't have any kind of 0 point energy. I hope you got this. Perfect? Clear? Okay, great. So now let me move forward to the other part of this section. So in the other part, I will be talking about some energy gap. So as I told you already, you are finding your energy gap in this way. You are just taking these values and you are just subtracting this. So if I tell you, okay, tell me if j equals to 99 and j equals to 15. So what will be the energy gap with energy gap of the corresponding energy level? That means corresponding this energy level. What will be the energy gap then? For that you have to like put values. That may be complicated. So energy gap can be calculated. It's in a very different manner. Okay. Let me tell you. Okay. Let me tell you. So energy gap. Now let me calculate energy gap. So if I talk about energy gap at a like for a certain energy level, like I am here, I don't know which energy level is this. I want to check the energy gap between the next two steps. Okay, so this is my one energy level and the next energy level is this. So because these two are new and next energy levels, so energy gap between two successive levels will be what? Delta E will be what? How can you calculate that? It's very easy. Suppose consider this is your j plus 1 level, it is your j level, right? So energy for j plus 1 minus energy for j, that will be energy gap, delta E. So how can you calculate your delta E? Your delta E can be calculated in this way. Like here if you just put your value E j plus 1. So you know expression of E means here nu bar. You know this expression, nu bar equals to B j into j plus 1. You know this expression, centimeter inverse. So in the place of j, as you are considering j plus 1, put j plus 1. So your expression will be what? Your expression will be B j plus 1, great. In the place of j, put j plus 1. Again j plus 1 plus 1. So you have put the value of this minus, again put the value of this. So again B and Ej means what? Bj into j plus 1, Bj into j plus 1. So this will be the energy gap of successive energy level. Okay. So from here you are considering here. So what will be the energy level? that energy level can be represented through this. If you do the subtraction, you will be getting delta E will be equals to B not B, 2B into J plus 1. Simple. If you do the mathematics. Okay. How can you do that? Okay, let me show you. Let me show you that basic mathematics. Okay. So now delta U will be what? Delta U will be, so take B into J plus 1, and then you will be having what? J plus 2 minus J. So minus J plus J will get cut. Epsilon equals to 2B into J plus 1. This will be the energy gap. In this way, you can easily calculate the energy gap of 2 energy level. Fine? Energy gap of 2 energy level. Simple. So this expression is very important in terms of IIT JAM examination. Even in NET GATE examination, this question comes from this part. Okay, that you are getting from this expression. Fine. So now question arises that, okay, fine, I am having this energy level, right? So this is one rotational energy level, this is another rotational energy level, this is another rotational energy level, another. So how one molecule goes to this energy level to this energy level? How? So that happens when you incorporate microwave radiation. Okay. Now my question is, how would you decide? How would you decide that energy transfer will happen from here to there, or here to there, or here to there? Where the like one molecule from which rotational level to another rotational level the molecule, like how would you decide that from this rotational level to which rotational level the molecule will go? How would you decide that? So the molecule can go from here to there, or the molecule can go here to there, or the molecule can go here to there, but the molecule cannot go here to there. So how would you decide that where your molecule can go and where your molecule cannot go? From which energy, like from which rotational level your molecule can jump to another rotational level, and from which rotational level your molecule cannot jump to another rotational level. So there should be some rule. Based upon those rules, you will be saying, okay, the molecule, the rotational energy level will follow this rule, and based upon this rule, I will be showing the transition, that from where transition is possible and from where to where transition is not possible, and that is called selection rule. Selection rule says that one molecule can jump from here to there or from here to there. So is it possible, or it's not possible? Selection rule will say that. So selection rule can be got by solving quantum mechanical calculations. So you have, if you do the quantum mechanical calculation for this, that you will be doing after going into IIT definitely. So then expression will come. That expression is called transition moment integral. Okay. So if you look at this expression will say which transition is possible and which transition is not possible. So this expression is actually mu. According to this expression, suppose one rotational energy level state is represented through psi I. Psi I is what? One rotational energy state. Rotational energy state. And from here you are moving to psi j. This is another rotational energy state. Okay. So whether from this energy state to this energy state molecule will jump or molecule will not jump, that will be decided by this transition moment integral, and that is represented through this expression mu ij, that is called transition moment integral, equals to integration of all space, because definitely in 3 dimension. Okay, whatever space is present in the corresponding quantum mechanical calculation, or consider only the integration. Fine. Then psi I star mu cap psi j d tau. Okay, and here this mu star, do you know what it is called? This mu star is called transition moment operator. Transition moment operator. Moment operator, right? transition moment operator. Fine. So by solving this expression, you will be getting that what transition or which transition are possible and which transition are not possible. So you have to solve this expression, this transition moment integral, and after solving this, you will be having two options. Okay, you will be having two options. If mu ij value, transition moment integral value is not equal to 0, then allowed transition. Transition may be allowed. Okay, and if mu ij value equals to 0, forbidden transition. Okay, so from this, if you calculate the values, you will be getting your selection rule delta j equals to plus minus 1. So delta j value will be plus minus 1. Suppose it is your one energy level based upon one j value. Okay, like j double prime I am considering, and you have another energy level that have that belongs to j prime energy, j prime value, right? So if j is plus 1, that means a rotational molecule will jump from this rotational level to this rotational level. Okay, that is delta j equals to plus 1. Delta j equals to minus 1 means one molecule will jump from here, this rotational level to this rotational level. Okay, so this is energy profile diagram. This is your energy profile diagram, right? E. Great. So here delta j will be minus 1. Fine. That means I already told you, if any molecule is going from lower energy level to higher energy level, what will happen? Absorption of energy. Absorption of energy. And after absorption energy, what you will be getting? You will be getting, let me write it over here. You will be getting absorption spectra. Okay, fine. And if the transition happens from higher energy level to lower energy level, then you will be getting, what will happen? Higher energy to lower energy. So the molecule will release some amount of energy. Fine. That because of that you will be getting, what will happen? Emission of energy. You will be having emission of energy. And because of that, what you will be getting? You will be getting emission spectra. You will be getting emission spectra. Simple. Okay. That's all. That's the thing. So I will be showing you how our absorption spectra is looking like and how our emission spectra generally looks like. Okay. So let me show you one by one. Okay. So the appearance of spectra. First of all, let me make the heading, the appearance of spectra. How the spectra appears. Appearance of spectra. How the spectra appears. So if I talk about absorption spectra, means here to there. So I have considered j double prime to j prime. Suppose I am considering this is my j value. So j double prime to j prime through absorption of energy. Okay. Fine. That means I can consider new bar j double prime to j prime. So it is higher energetic, it is lower energetic. That I have already shown you. Higher energetic, lower energetic. So this transition, that means j double prime to j prime. What will be the energy gap? Energy gap will be epsilon or nu bar j minus nu bar j double prime. So nu bar j prime minus nu bar j double prime. This will be the energy gap for this transition. Fine. Simple. Therefore, I can write one thing. If I put the value of this j prime, so I will be getting this expression p j prime plus 1. Yes. And if I put this value, so b j double prime plus 1, I will be having this. Simple. I have put just values. Okay, so if you do the calculation further, you will be getting b j prime plus 1 and minus again j double prime plus 1. You will be getting this kind of expression. Okay, and this expression will give you the unit in centimeter inverse. Okay, unit in centimeter inverse. Perfect. So that's all. That is the expression from which I will be showing you absorption and emission spectra. Okay. So whenever molecule is jumping from here to there, I mean from J double prime to J prime ABS, you are getting absorption spectra. How it is looking like? So let me talk about absorption spectra. Absorption spectra. Okay, absorption spectra. So in case of absorption, what will happen? I told you already, in case of absorption delta J will be plus 1. So if your delta J equals to plus 1, then I can write that absorption is happening from here to there. So this value is what? Plus 1. This difference is plus 1. Difference means J prime minus J double prime, larger value minus smaller value will be plus 1. So I can write J prime minus J double prime will be plus 1, right? I can write in this way. This is the difference. And finally I can write, therefore J prime equals to J double prime plus 1. Yes, in this way. That means this is my higher value, this is my lower energy J value, right? Higher J value, lower J value, and this is happening for absorption spectroscopy. That means I can say, and the difference is what? Difference in between these two difference is what? Difference is 1. Difference is 1. That's the selection. That selection rule says. So I can write this expression in this way as well. J2, I am considering this transition is happening where? J2, J plus 1, and if you calculate the difference between 2, you will be getting 1. So this difference is also 1, this difference is also 1. So I am considering that, okay, transition is actually happening from one J level to next J plus 1 energy level. I can consider that. Yeah. So if you take this one, and now if you again calculate nu bar J2 J plus 1, what will be your expression? Let's have a look at that. So nu bar J plus 1 minus nu bar J. So if you put the value B J plus 1 J plus 2 minus B J into J plus 1. Okay. So from here what you will be getting? You will be getting B J plus 1 and finally J plus 2 minus J plus 2 minus J. That means B 2B J plus 1, and that is the value that we got initially, like the energy difference, right? Energy difference value. Yes, this value. Same value I am getting, and that I should get. That means it is perfect. The calculation is perfect. This will be my this centimeter inverse. So now how would I show what will be my absorption spectra? How would I show that? Fine. How would I show that? What will be my absorption spectra? So whenever a molecule will jump from one rotational level to another rotational level, I will be having this energy gap. Because my delta J value plus 1. It cannot be plus 2. This energy level, it can jump here to there or here to there. It cannot jump here to there. That will be plus 2. It is not possible. It is not go further. It cannot go further because your selection rule is delta J equals to plus minus 1 according to rigid rotor model. Remember, rigid rotor model. According to rigid rotor model, I am talking about rigid rotor model. Okay. So this is your value that you are following. Now simply what you need to do, if you want to calculate your value for like different systems for different energy levels, then it will be better. Fine. So let me calculate one by one those. So if my transition is happening from 0 to 1 energy level, 0 to 1, so B value will be 0, so 0 to 1, that will become 0, J value will be 0, so 0 means 0 plus 1, 1, 2B, so your energy value will be 2B. For this nu bar will be 2b centimeter inverse, right? If we put value 0 over here in the J value, if you put J value 0, it will become 2b. If you put like 1 to 2, because only delta J can be what? Plus minus 1. From 1 to 2, you will be having 4b. Here you can put 2, here you can put 1. If you do calculation, so J means what? J means 1, so put 1. J means 1. Okay, 1 plus 1, 2, 4b. If you do similarly, nu bar equals to 2 to 3, you will be getting 6b centimeter inverse. Nu bar 2 to 3, 3 to 4. Then you will be getting 8b centimeter inverse. So in this way, you will be keep on getting your values for absorption spectra. For whenever energy absorption will happen and molecule will jump from one lower rotational level to another higher rotational level. Perfect. So now if I show you the energy profile diagram for this, if I show you, this is my energy profile diagram. Okay, and here I am putting the value of, rotational quantum number, that means J value. Here I am putting value of nu bar, that is in centimeter inverse. Okay, then here I am putting rotational energy level. Okay, here I am putting position of spectral line. Here I am putting spacing between spectral line, gap between spectral line, Perfect. Simple. So now if I put J value 0, 1, 2, 3 and 4 in this way, so I will be getting a value 0, then 2b, then 6b, then 12b, then 20b. Yes. So if I calculate the difference, so these are my energy levels. Yeah. Yeah, now it's fine. These are my energy levels. So 0 means this, 2b, 6b, 12b, 20b. So what is the difference between these two energy levels? So it is 0, energy 0. So this energy gap is what? This energy gap is 2b. This energy gap is what? 4b. This energy gap is what? Like 6b. This energy gap is what? 8b. Okay, so these are the position of energy line. Position means what? Suppose I am drawing a spectral line. How a spectral looks like? This and this. Here you show intensity. Okay, and here you show J value in centimeter inverse. J value, right? So if you put J value, okay, generally if you put J value, so look at this. Your energy level will keep on increasing. So first of all, it is your 2b. So it is a 2b position, right? 2b. So suppose it's starting with 0. This 0 value. Okay. 2b means here 0 to 2b. So the position of this spectral line is 2b, right? Then 0 to after 2b, the next position is 4b after 4b distance, right? So the distance will be 4b. 4b position. So 0 to 2b, another 2b, 4b. Then what? Then 6b, then 8b. 6b means here 6b. Then here 8b. In this way, you will keep on getting your spectral lines. Simple. So 0 to 2b, 4b, 6b, 8b. Energy increasing, spectral line is having same thing. Okay. Now, if you look at the spacing gap, if you look at the gap, what will be the gap? To calculate gap, just take the distance. What is the distance? 2b. Take the gap, distance 2b. Take the gap, distance 2b. So every time you are getting same distance, like this distance, this distance 2b, 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 right? That means what is happening over here, you are getting like same spacing, same gap between the energy level, like in the spectra. So your real spectra generally looks like this. Whenever you will be doing experiment of with microwave spectra, your spectral line will be looking like this, and in this spectral line, you will be having 2b distance, 2b distance, 2b distance, and you will be keep on getting this distance 2b. That means your spacing is same, gap between line is same, it is fixed 2b every time. Look at this 2b. But the energy is different. So this line is at 2b energy level, 2b position. It is 4b, it is 6b, it is 8b, and 2b, 6b, 4b, 8b with respect to what? With respect to this point 0. Okay. This distance 2b, 4b, 8b, 6b, 8b. 2b position. I am talking about position. Okay. 2b position, 4b, 6b, 8b position. And these are what? These are just energy levels. Don't think it is 0, it is 2b, it is 6b. No. This is just energy level. These are not position of the like spectra that you will be getting like from experiment. Okay, simple. So from here you are getting what? You are getting this kind of lines. Now you can ask me one question, why I have drawn this line? Why I have drawn this line? Like height is less, height is more, height is further more, and this. Actually this is decided through the population of energy state. Okay, population of energy state. So look at this. This is my absorption spectra. Absorption spectra means, so for 6b I have written more height. I have given more height. That means whenever any transition is happening, so the 6b energy level, the 6b state, this energy state, okay, this becomes more populated or maximum populated over here. Maximum populated means at this state maximum number of molecules are present. At this energy state, at this position, maximum number of molecules are present. That's why it has more height. More height will means more intensity. So the height can be decided through the population. Okay. Now just understand this thing. So if maximum number of molecules are at this level, height will be more. Here height is less because less number of molecules are present at this level. Simple. Okay. So this height means population. So more population, more height, more population, more height, more height, more intensity. So this is the energy, this is the plot for absorption spectra. So now if I do the same calculation for emission spectra, what I will be getting? Emission spectra. If you do the emission spectra, you will be getting same rule. For emission spectra, as I told you already, delta J value will be -1. Right? It will be -1. So now if I do -1, that means from this level, this level. So it is my J plus 1 level, it is J level. So molecule will come from here to there. Delta J will be -1. -1 means higher to lower. J plus 1 minus like higher to lower energy level. If it is coming in this way, then I will be saying delta J will be -1. So 1 is decreasing. So that's why the difference is -1. So this is my final, this is my initial. So final minus initial, what will happen? Final minus initial, that is the delta J value. Right? So final is J, initial is J plus 1. What? J minus J minus 1. -1. That's why your delta J value is this, -1. Clear? So if your delta J value is -1, what kind of plot you will be getting? Okay. So for that, what I am doing, I am just showing you the values. Okay. So transition generally happens from J plus 1 to J in case of emission spectrum. In that case, you will be getting what? Final, which final one is this? So final energy state like J minus initial J plus 1. So final minus initial, what you will be getting? So B J into J plus 1 minus B J plus 1 into J plus 2. Simple. Okay. So now B J into J plus 1 If you take common, so you will be getting B into J plus 1 J minus 2. That means what? Minus B J plus 1 minus 2B J plus 1. This is the value, right? This is the value in whenever you are considering emission spectrum. Fine. This is your value. Now if you consider this value and draw your same kind of diagram like rotational energy level, like J value, rotational quantum number J, then energy level, okay, then position of spectral line, am I missing something? Then rotational energy level, okay, value of nu bar, okay, it will be second one will be value of nu bar, rotational energy level, okay, after energy level position of line, and finally you will be having gap. Fine. So if you put corresponding values 0, 1, 2, 3, 4, look at this, gap is also increasing, right? Because energy value will be increasing. So for this you will be getting 0 value, then 2B value, then 6B value, then 12B value. These are the energy values, nothing else. 20B values. And your energy level will be this and this, okay. After that, now you are talking about emission. That means molecule will jump from here to there, here to there, here to there, here to there. And what is the energy gap? What will be the position? So if it is going from here to there, 4 to 3, so J value is 3. So if you put 3 plus 1, 2, 6, minus 6B, 4 to 3, okay, 4 to 3, okay. So if you put here 4 to 3, it will become what? 3 plus 1, 4 into 2, 8, minus 8B, minus 6B, minus 4B, yes, and minus 2B. So I am just subtracting this value. Gap is this 2B, 4B, 6B, 8B. 2B, 4B, 6B, 8B, right? These are the energy gap values because it is emission, so that's why a molecule is coming from higher energy state to lower energy state, right? Because that's why emission of energy will happen. Clear? So if you calculate the energy gap, I mean spectral gap, so you have to take this value, this value, this value. This is your what? 2B value, 2B value, 2B value. So here you are getting every time gap is 2B. So because of that you will be getting same kind of plot. It is your intensity. And your plot is starting from 0, 2B, 4B, 6B. Okay. Then like this 0, 2B or minus 2B. It will be minus 2B, minus 4B, minus 6B, minus 8B. So what is the energy gap here? Here the gap is 2B, here the gap is 2B, here the gap is 2B. Clear? This is your energy gap. So this is here also again this state is mostly populated. That's why its intensity is high. So that's the thing about also emission spectra. So from here what conclusion you are getting? You are getting one conclusion that these energy levels, if you look at these energy levels, these are called energy levels. These energy levels are not equispaced. The gap between the energy level is not same. Here it is 2B gap, 4B gap, 6B gap, 8B gap. Gap is different. So gap between energy levels are different, but remember spectral gap, this gap is not energy gap, this is called spectral gap. spectral gap. That means gap between these two line in spectra, in microwave spectra, this gap is same, but gap between spectral lines are same. Fine. So this conclusion you are getting. Okay, this conclusion you are getting. So yeah, so if you want to calculate the what will be the height, for that, yeah, experimentally you will be getting that, but theoretically you will be having some process. So now question arises, how would you understand that which state will be more populated and which state will be less populated? How would you understand that? And that can be understood, or what will be the intensity of that corresponding line. You know that you will be having one line here, another line here, another line here, and finally another line here. So now how you would decide what will be the intensity of that spectral line? How would you decide that theoretically? So that we will be understanding in the next video, that is about transition, that we will be understanding through transition probability, and second is about population of state. So through these two factors we will be trying to understand that how this height can be determined theoretically. Fine. So this transition probability and this population of state, these two factors will be responsible for the intensity of the spectral line, the height of the spectral line. So don't mix the energy level and spectral gap, energy gap and the spectral gap. This is my energy gap of different rotational energy level, and this is my what? Gap between two spectral line, this gap. Clear? So that's all about this video. So in the next video we will be talking about this transition probability and population of state, and how we will be deciding the height, the intensity of the spectral line. Simple. Got it? So do you have any question regarding today's lecture? Got it? So this formula you need to remember for that. This formula is very important. This delta G will be plus minus 1, then this formula this energy gap formula, and finally whether 0 point energy is present or not, this one, and finally this one, nu bar equals to Bj into J plus 1 centimeter inverse. These formulas are very important. So did you understand? Any question if you have, you can ask me right now. If you have any question, you can ask me right now. Okay then. So we will be meeting in the next video. Till then, goodbye. Bye bye. Good night to all of you. Okay, still understood. Okay, fine. Yeah, great. So meeting you soon in the next video. Till then, goodbye. Okay, bye bye.